Welcome back. This is the last video of this week's lecture. We are going to have a brief reminder of simple linear regression models. Here, the equation y equal to beta 0 plus beta 1 times x plus u is a simple linear regression model. It describes the relationship between two variables, x and y. We often use it to explain how the variable y changes with the variable x. The variable y on the left-hand side is the dependent variable. It is also called the explained variable or the regressant. The variable x on the right-hand side is the independent variable, or we can call it explanatory variable or the regressor. The parameters beta 0 and beta 1 are the ones we want to estimate. Beta 0 is the intercept parameter, and beta 1 is the slope parameter. We often focus on this beta 1 here because it directly tells us how much y changes when 1 unit of x changes. The u is the error term. It includes all unobserved variables. Besides the variable x, many other factors may also affect y. But if we cannot observe them, we just put them in the error term and make some assumptions about this u later. Now, based on this simple econometric model, we can collect data and estimate the parameters. How can we make sure that the estimators for beta 0 and beta 1 are reliable in describing the relationship between x and y? We need assumptions. These assumptions guarantee that under certain cases, the estimated relationships are reliable. What are these certain cases? The first assumption is that we have the correct specification. In the first video, I've already showed that sometimes we have to check the data and check different specifications, whether we should use y and x here or we should do some transformation. For example, should we consider log y and log x? The second assumption is about this random sampling of the random sample of size n. This random sampling is quite common for cross-sectional data. It means that if we have a sample, suppose it is 100 observation of housing prices and sizes of each house, this sample is randomly drawn from the population. You can imagine the population is all the prices and sizes of the house in the whole world. The third assumption is that we need some variations in x. This one is very simple, very easy to understand. If there is no change in x, we cannot tell whether the change in y is caused by x or not. The last assumption is that the conditional expectation of the error term u is 0. So what does that mean? It basically says that with the control of x, the influence on y from all other unobserved factors is 0 on average. It can be the case that some unobserved factors increases y and some unobserved factors decreases y. But on average, they just cancel out and the average effect is 0. Under these assumptions, the ordinary least square estimation will give us unbiased estimates of beta 1 and beta 0. Here is an example of the simple linear regression models. Suppose I want to know how the expenditure on food vary with the household incomes. I can build an econometric model. The dependent variable y is the food expenditure, and the independent variable x is the family income. In microeconomics, this relationship is also called an angle curve, and its slope should be positive. Rich families should spend more money on food. That makes sense. Now I have the data called food.dta. It is a data file with household data on weekly income and weekly food expenditure. How can I check their relationships? Here is the code in R. First, I need to call the package called foreign. One of the functions in this package is read.dta, which I can use it to read the data file. And let's call this data file food. The data set has two variables, food expenditure and income. You can use the head function to check what the data looks like. You can also check the mean and some summary statistics of each variable. For example, here is the mean of food expenditure is around $283, and the average income per week is around $20,000. So what about the relationships between these two variables? I can first plot them. It will give us a brief idea about their relationships. Here is the figure. The x-axis is the income, and the y-axis is the food expenditure. Each point in this figure is an observation. For example, for this point here, it means that there is a family. The weekly income is around 16,000, and the weekly expenditure on food is around $300. If you only check this scatter plot, there is a positive relationship between income and food expenditure. But if we want to estimate the parameters if we also estimate the parameters in the regression model, then we can say more about their relationships. We can even predict the food expenditures for families that are out of this sample. How to get the OAS estimators? The basic idea of linear regression models is to find a line that captures the relationship between x and y. For a specific value xi, we define a fitted value for y, which is the yi hat here. Yi hat equals to beta 0 hat plus beta 1 hat times xi. But this fitted value yi hat may not be exactly the same as the yi we observe from the data. Let's define the difference between them, yi minus yi hat, as a residual for this specific observation. For each one of the observation xi, yi, we have one residual ui hat. In total, we have n observations and n residuals. The average distance between this observed y and the fitted yi hat can be summarized by the sum of squared residuals over the whole sample, which is here. If we pick beta 0 hat and beta 1 hat, that makes the sum of squared residuals as small as possible. We can make sure that the fitted value yi hat is close enough to the observed value yi hat. This will support the relationship we proposed, which is yi hat equal to beta 0 hat plus beta 1 hat times xi. It means that the proposed line is reasonable to capture the true relationship between y and x. In other words, this is our objective function. We want to select beta 0 hat and beta 1 hat to minimize the average distance between the observed y and the fitted value yi hat. Here is a graphical illustration of the OAS estimator. Like in previous example, each point in this figure is an observation in the sample. It has a value of x and a value of yi. For each x, we assume the fitted value yi hat equal to beta 0 hat plus beta 1 hat times xi. So So if you plot this relationship, it will be a line in this figure. So it means the yi hat is actually here. This is the point for yi hat. So for example, it's here. It means that the residual is the distance here, which is the residual. If you do it for each observation, we can find out that some residuals are positive. For example, like the case here, this is a positive residual. Some residuals are negative, like this is a negative residual. But if we use the squared residuals, it does not matter whether the residual is positive or negative. The best beta 0 hat and beta 1 hat should make the sum of the squared residuals as small as possible. We continue to solve the minimization problem by looking at the first order conditions. If we take partial derivatives of beta 0 hat and beta 1 hat of equation 3, we will have these two following equations. So remember that equation 3 is the minimize the summation from 1 to n, and which is the square sum of residuals, which is yi minus beta 0 hat minus beta 1 hat times xi square. So if you take this partial derivative for beta 0, it shows only here, so it has like a minus 2 times the summation of this whole equation here. And if you take partial derivative of beta 1 hat, it shows up here. So besides this term, we only have like xi here. So notice that how to solve these two equations. First, notice that the equation 5 can be simplified. First, this minus 2 doesn't matter. So if we split this summation here, we have summation over yi minus summation over beta 0 hat minus summation over beta 1 hat times xi equal to 0. So if we divide the whole equation by the sample size n, we will have the sample mean of y equal to, here is just the beta 0 n beta 0 hat, divide n is still equal to beta 0 hat, plus beta 1 hat, doesn't matter, and also the summation over xi is the sample mean of the independent variable x bar. So this is the simplification of the equation 5. If we plug this equation 5 into the second equation 6, then we will have that we can further simplify the equation 6. So here is how can we do it. So the beta 0 hat is equal to y bar minus beta 1 hat x bar. So if you plug this relationship here, then we will have summation yi minus y bar minus beta 1 hat x bar minus beta 1 hat xi times xi equal to 0, which is exactly the equation 9 here. You further simplify this equation, so it's equal to the summation xi yi minus y bar minus beta 1 hat xi minus x bar equal to 0. You just put this term on the right hand side, then you get this the equation 10. So we can solve this beta 1 hat, which is the left hand side, divide the right hand side here. So here is the Therefore, the beta 1 hat can be written as beta 1 hat as the divide of these two terms. So remember that beta 0 hat equal to 1 bar, a y bar minus beta 1 hat x bar. So after you get this beta 1 hat, then you can also get this beta 0 hat. Here are some properties of the summation operator. It turns out that the numerator of this beta 1 hat is equal to the variance of xi. So why is this the case? If we split the variance of xi, it's equal to the sum xi minus x bar times xi minus x bar is equal to sum xi minus x bar times xi minus x bar times this xi minus x bar. But if you check this out, this term is equal to 0, so we only have this part left. And similarly, if you split the second term, the denominator is the covariance between x and y. So therefore, we can rewrite beta 1 hat as the covariance between x and y divide the variance of x. So the estimator beta 1 hat is simply the sample variance between x and y divided by the sample variance of x. So it's very easy to remember. Once you have this beta 1 hat, then you can replace the beta 1 hat, go back to the equation 5, and we have this beta 0 hat. Another implication of this equation 13 is that the variance x is always positive. So if the correlation between x and y is positive, beta 1 hat will be positive. Before moving on, I would like to talk a little bit about the regression functions for population and for the sample. Recall that the econometric model we built, y equal to beta 0 plus beta 1 x times plus u. So if we take expectation of y conditional on x, we have expectation of y conditional on x is equal to beta 0 plus beta 1 x plus 0, because the assumption for expectation of u conditional on x is 0. This equation is called the population regression function. The relationship is fixed and unknown. You can think it as the true beta 0 and beta 1 you can get if you can get all the data and control everything in the world. But we still want to know this beta 0 and beta 1, so we collect a data sample and estimate beta 0 and beta 1 through the sample regression function. This is the sample regression function y hat equal to beta 0 hat plus beta 1 hat times x. The estimated beta hat may not be exactly the same as the true parameter, but we still want them to be reasonable and to be a good approximation for the true parameter. Therefore, we try to get these beta hats by minimizing the distance between the observed y and the fitted y, or fitted value y hat. But notice that these estimators all depend on the sample. If we estimate them with a new sample, we may have different values of beta 0 hat and beta 1 hat, but the true betas are fixed. It's just no one knows them. Okay, that's all for today's video. Next week, we will learn more about the linear regression models.